everyone. Thank you so much for joining both in this little viewing area that we have on campus, but then also everyone online. Part of this, the great thing about this seminar is to be able to make it accessible not just at UW, but all over the world. And it is my pleasure to introduce today our last speaker of the term, Professor Sam Taira from UCLA. So Sam is a world expert in fluid dynamics and actually was named one of very few recipients as the Vannevar Bush Faculty. And this is one of the most prestigious honors that you can actually get from the US government. So um, it's an incredible honor to have you here today, Sam, and you'll be talking today about extreme aerodynamics. And we're just so excited to hear what you have to say. So with that, I'll let you take it.
Great. Thank you, Nick. Thank you for the very kind introduction and for inviting me to speak in front of you guys. I'm looking forward to receiving feedback. I'm a fluid mechanician or aerodynamicist by training, and I am very open to using data-driven techniques to solve some of the problems that we have. So I want to get some feedback from you all to see how we can do better or maybe even work on this exciting problem together. So like Nick said, this is supported by the Department of Defense under the Vannevar Bush Faculty Program. And it's been something that's been keeping us quite busy for some time now. Okay, so let me get started. Before I get started, let me acknowledge a few people, or actually a group of people. There's been an army of students and postdocs that have been involved in our effort. Kai, Luke, Hiroto, and Vinasri are some of the main people who are involved. Many of them have moved on past UCLA to join as faculty or now postdocs. And of course, there are many more people who are not on this list. We also have a wonderful group of collaborators that we get to work with. Steve, of course, has been a longtime collaborator on some of these topics. And we've been very fortunate to get a lot of support from our program managers at the Department of Defense, Greg, Doug, Matt, and John-Luc. Okay, so let me get started. So I'm going to talk about extreme aerodynamics, but before that, you all fly, right? You all have flown on airplanes, and there are very different kinds of airplanes that serve different roles in our society. Some of you might have seen some of these airplanes. They come in different shapes, sizes, and they have different ways of keeping themselves aloft in air. But I'm not going to talk about most of these airplanes today, right? I'm going to talk about something that's quite different from a lot of these airplanes. By the way, a lot of these airplanes fly in cruise conditions, so they're mostly operating in what we would call a steady or quasi-steady condition, okay? Right, so when we talk about the airplanes that I just spoke about, this is what we think about, right? Obstacle-free environment. This is a picture I took out of a window from one of the Delta flights that I've taken. This is at LAX early in the morning. And you can see that there's no clutter around the airfield, right? So there's no obstacles around it. And there are strict rules about where you can have obstacles, how far it needs to be from the airplane. Okay. And we tend to fly in favorable weather conditions, or we want to, right? So here's a picture of, or a snapshot of all the flights that were taking place on a certain day. I used to work at the Florida State University, and you'll see Tallahassee right here, but you'll probably notice that there's a big void in this area over northern Florida and Georgia. Can anybody guess what happened there? Does anybody know what happens? It happens quite often over the let's say the year. What happened here was there was this gigantic vortex called a hurricane, right? And when you have adverse weather or weather events, you kind of want to avoid that if you want to stay safe in the airplane or maybe not be bounced around. Okay. Now, you have heard of wake turbulence. These unsteady air or strong vortical features in the air are quite violent. Okay. Here's an A380. That's flying, and you can see behind it is two counter-rotating vortices that are pretty strong. A380, if you have seen it in the past, is a pretty giant airplane, right? And what happens is it generates a big signature behind itself as it's flying. Now, you certainly don't want to fly anywhere near those wake vortices, but there was an unfortunate incident over the Indian Ocean where a Challenger 640, an aircraft that's much smaller than the 380, flew into those wakes a few miles downstream. The wake vortices are pretty strong. They're persistent. They will last there for a while. The weight difference between a 380 and a Challenger 640 is about 25 to 1. So it's lightweight compared to a 380. And if you fly into the wake of one of these, bad things can happen. And by the way, don't think this is only for rich people, although that is a private plane. That's the same thing as well. That plane also serves as regional jets. So you might have flown on actually one of those planes as well. Here's what happens before and after. This plane flew into the wake. Before, I don't know if this is the exact picture, but I'm sure it was a very nice chartered flight. But afterwards, the plane went upside down, bounced around, and you can see bloodstains all over the cabin. There were some critical injuries. Luckily, no one died, but this plane was written off afterwards, and it miraculously did not crash into the ocean and landed somewhere in the Middle East. So you can see that these wakes that these airplanes make are significant in its strength, and it can disrupt flight safety. Okay, now what I'm going to talk about today is not those big planes. I just wanted to illustrate the point that these wake vortices are pretty strong, right? Now, let me talk about modern low-speed aerodynamic problems, where we would have many scenarios in which flight operations are restricted. For example, you might have heard of air taxis, right? But think of trying to fly an air taxi on a bad weather, where you have strong winds that would generate a wake behind a building. Now, you might be thinking of flying a drone too for certain reasons, but you can imagine that now those vortices are pretty strong and larger than the vehicle that's trying to fly, okay? Another instance is when you're trying to perform rescue in a mountainous area when it's a windy day. You can imagine that the wind speed could be large, the vortices or the wake structures behind a mountain will be maybe perhaps even larger than the vehicle that you're trying to operate. In fact, this is one of the major reasons why rescue missions are still restricted because of weather, okay? Another thing that might be interesting to consider is what happens if you want to try to land an aircraft or a helicopter behind a ship, right? The ship itself is a large structure. It generates a wake itself. And if you want to, if you want to land a helicopter or a rotorcraft behind that ship, it is really landing right straight into those vortices. And this is a huge problem, not only for manned missions, but also for autonomous systems where it's trying to maneuver itself with limited sensor measurements. Okay. All right. So why is this challenging, right? And I'm going to talk about why we are excited to use machine learning and data science for some of these problems or many of these problems. Now, first of all, before I talk about the overall problem setup, let me talk about why we haven't really worried about this, right? If you talk about a commercial airliner and maybe you experienced a gusty condition or turbulence, so-called turbulence, and your coffee spilled, it really is not going to compromise the safety of the flight. Okay, it's uncomfortable, but it's not a big deal. One of the parameters that's important here is called the gust ratio, the characteristic velocity of the gust that hits the aircraft to the cruise speed of the vehicle. Now, because large aircraft fly so fast, the gust ratio is really low. As you make your aircraft smaller and slower, this gust ratio starts to approach 1, and that's when things become a little uncomfortable, right? Because now the gust ratio is so high, at some point, you're going to lose the stability of the aircraft. In fact, anything beyond gust ratio 1 is traditionally considered unflyable, okay? All right, now please interrupt me if you have any questions. I'll be happy to answer at any time. Okay, and in this talk, I'm going to talk about aircraft that looks kind of like this. We're going to model the behavior of the aircraft with a straight wing that will be flying all over the place at very high angles of attack. Okay, and again, this gust ratio is pretty important, and as I kind of hinted, and when the gust ratio exceeds 1, the role of the disturbance and the vehicle switches, And in this talk, I'm going to refer to aerodynamic problems with gust ratio larger than 1 to be extreme aerodynamics. Okay, so that's where the name extreme comes from. Okay, so let me explain a little bit more about why this is challenging, not just from the aerodynamics point of view, but also from the point of view of analysis. Okay, we are pretty good at designing airplanes now as engineers, and you are benefiting from these airplanes as a society, right? So there's a base condition, which is identified or signified in black, and there's some perturbations around that base state, but you can stabilize the flight dynamics, right? That's what you would see on a 777 or maybe a fighter jet. Now, if you want to move beyond that, you can look at quasi-steady aerodynamics. Let's say you're brave, you want to fly into those hurricanes as a hurricane hunter, the base flow or the base conditions around the vehicle is changing, or maybe you're changing the shape of the vehicle as you're flying, like a V-22. In those cases, the perturbations are still small and there's the base flow around it. Now, what we're considering here in extreme aerodynamics is when the base flow is violently changing, and also the disturbance around that flow is also changing, and those magnitudes are now becoming equivalent, almost in size. So think of the spatial scales and the temporal scales now being very difficult to distinguish between the base flow and the disturbed flow now. Okay, so you would imagine linear theory is really not going to help much in these cases. This is where the major challenges comes from when we start looking into extreme aerodynamics. But you can imagine now this is really critical for us to understand if we want to make a breakthrough in flying in these highly unsteady environments. Okay, so what are the really big challenges? I said earlier, extreme aerodynamics, we deal with large amplitude disturbances. They're not really perturbations anymore. So linear theory is likely not going to work in many cases. The dynamics are inherently transient, and I'm going to come back to this later. So we usually deal with steady flows or periodic flows, but how do we deal with transient cases? That's going to be important. We also need to choose appropriate model problems, okay? Time varying base flow needs to be considered. That means we need to consider a large parametric sweep that will require an enormous amount of computations and experiments. So this goes back to the model problems, right? We do need appropriate model problems chosen, and we need to capture an appropriate parameter space that would capture the important physics that we're trying to understand. Okay, so this requires us to analyze a massive data set, as I'll show later. Okay, even for a simple problem, this quickly leads to a massive data set. And from that massive data set, we want to extract the physical insights. We can't extract each and every little detail, but we want to get the key dynamics, the low dimensional behavior of extreme aerodynamics, right? And given that notion of dynamics, as an aerodynamicist, I'm interested in making sure these airplanes can fly. So that means we need to gain situational awareness around the aircraft in real time and act on that information so that you can control the flow or control the vehicle. And that needs to happen fast. Okay, so these are the challenges associated with extreme aerodynamics right now. Another big thing is if you want to fly in real turbulence or atmospheric turbulence, then there are really a huge variety of disturbances that an aircraft can be hit. And I'm only going to consider a few of these that I'm going to show today. Okay. All right. So let me start with a very seemingly simple example. Okay, here we have an airfoil or a 2D wing that's going to be hit by a really strong vortex. So this vortex is rotating and it's approaching this wing. It's laminar, so the Reynolds number is 100 in this case. And you could say, well, it seems like a simple problem. But this quickly gets out of hand because the vortex strength, the circulation, the size of the vortex, the position at which the vortex hits the wing, the profile of the vortex, right? The angle attack of the wing, the shape of the airfoil, the phase, the timing at which this vortex hits the wing. These are also, they can be varied. If you want to go further, you can also consider what happens when the Reynolds numbers change, the Mach numbers change, or if you have noise around the wing. Right. Another thing you can think of is, well, these movies show a single vortex hitting, but what happens if you have multiple vortices? Okay, so if you were to map out this data set, even for 3 variables, let's say, or actually this is 4 rather. This is the angle attacks are changed in different plots. The D is the size of the vortex, G is the gust ratio, how strong the vortex is, and Y naught over C is just the initial position at which the vortex hits the wing. These dots in these scatter plots are showing a single case, but each case holds a simulation of the flow field, the unsteady flow field, right? So yeah, it gets quickly out of hand, right? All the data becomes really large and you start filling up your hard drive pretty quickly, okay? All right, now let's look at these flow fields a little bit, okay? So I have a lot of information, so bear with me, but here in this column that I'm going through, let me see if we can show the laser pointer here, okay? These are the cases without any disturbances hitting the wing. Okay, these are pretty simple 2D flows. Initially at a lower angle attack, it's steady. As you increase the angle of attack from 20 to 60 degrees, you'll see that you'll get this Kármán shedding, right? Periodic orbits, really, okay? And the lift for these undisturbed cases are shown in dashed lines in the plot to the left. Okay, these are lift history over time. The plots on the right shows the vorticity field. Okay, just the amount of rotation you'll see in the flow field when it is being hit by a particular vortex. And those are highlighted by circles and triangles over certain trajectories or lift histories, okay? And beyond the cases that we're showing, there are also other cases that we're showing just for comparison. Those are in the lighter state of curves, okay? So there are a lot of different cases overlaid here. And you'll notice that it's all over the place, okay? There's no simple linear scaling that you can perform to collapse the data easily. This is not something you can easily do. However, as humans, there's some hope, right? If I were to stare at this flow field as a fluid mechanician, I can tell where a vortex is. I can tell where a shear layer is. I can tell whether it's separated, whether attached, right? Or whether there's a secondary vortex forming. So I can pull out these features. So I'm very hopeful here that there might be a way to mathematically pull out these low dimensional behavior, okay? That's my starting point. Now, the first thing we tried, because we love our modal analysis, I suppose, we said, well, why don't we do PCA or POD on the entire data set? Okay, so you got all these snapshots. Let's just collect all the snapshots and see what we get, right? And based on those snapshots, let's see how well we can reproduce the flow field, the vorticity field. I'm showing the coefficients, right? Temporal coefficients of all these data sets for the first 3 coefficients, that is the dominant 3. And you'll notice that you'll get this big blob of data. The color represents the angle attack. In fact, initially at 20 degrees, it's a steady flow, so it's just a dot. It goes to the other side and so on and so forth. But it's kind of a big blob. If you try to reconstruct a flow field, it doesn't really do a good job. If you consider this POD reconstruction using a few modes, this is the reconstruction error. It's 130%, and you will see the artifact of where you saw the wings position. Okay, and you can't even predict where the large vortex is hitting the wing. Okay, all right, fine. We didn't really expect this to work. So the next thing we tried was, well, why don't we use an autoencoder, right? So the autoencoder, as you all know, there's a convolution area in particular for this example because we're dealing with a snapshot, right? And then that's connected to a multi-layer perceptron. There's a bottleneck in the middle, and then we expand it out. So this is a compression that we're trying to see if there's a low-dimensional representation of all the snapshots that are shown across angle of attack, across strength, across positions, et cetera, et cetera. Okay, and to our surprise, it worked pretty darn good. Okay, the data is, again, it looks like a spaghetti field, right? It's all over the place over time. But when you look at how well you can reconstruct a flow field from a very small number of variables, it did extremely well. I'm talking about hundreds of cases. I'm not talking about a few cases. We're talking about hundreds of different cases. And across the board, it works really well with about 20% difference or error. And you might think, well, 20%, is that good or bad? We consider that to be excellent because we can now pull out features of the vortex that's hitting the wing, the secondary vortex that's being generated, the wake structures, and et cetera, et cetera. Also, these things track very well in time, okay? However, one of the challenges that we have is that we now are able to compress it down to 3 variables, which is amazing, right? All that information being represented by 3, but we can't really comprehend what this means in the latent space, okay? So what we done was that we introduced a simple fix, or a simple, I would say, extension of the original autoencoder. We said, well, we know the flow field, the omega, right? The vorticity field is intimately tied to lift. And as an aeronautics engineer, I care about lift because I don't want to crash into the ground, right? So if I know that information, what if I say, well, I want xi, the latent variable, to make sure that it knows something about lift? Now, this was an excellent thing to try because you can now perform this optimization problem. We're now trying to match lift as well, okay? That ensured that we're capturing the vertical structures that contribute to lift or highly correlated with lift, okay? And by the way, we tried this setup for different types of problems. It works really well if you know what the right variable is that you care about, right, for the physics. Okay, so if you do that now, the data collapses onto a nice shaped manifold, right? Like this cone, okay? The baseline cases are shown in these colors, and all the disturbed cases are shown in gray. So the gray one wraps around this nice cone, okay? And the reconstructions, it gets slightly worse than the original autoencoder model, but it does still a really good job reconstructing the flow field, capturing the flow field. So all that information I talked about, all the the big data set, now it's only down to 3 variables, right? Now, some of you might say, well, is it really 3, right? Okay, so I'll talk more about this later, but this to us was interpretable, okay? These axes, xi1 and xi2, really captures the periodic nature of the shedding for the baseline flow. Okay, it also tells you that as you go further away from this dot, or this the radius that is, the larger the radius, the more fluctuations you'll see in the flow field, right? So you'll see more vorticity entering into the flow field. If you go up in the third direction, that tells you that there is a effective angle attack of the flow. And those of you who are in fluid mechanics will know that effective angle attack has a close relationship to lift, right? So if you go upward in this direction, on the xi3 direction, you're increasing lift, or you're temporarily increasing lift as if the angle attack is increasing, okay? So a lot of the information that we were able to get from this nonlinear autoencoder augmented by lift now tells us a lot about the dynamics now, and everything's wrapped around here. So it could go up, down, et cetera, okay? So just to give you an idea, these are cases that we looked at afterwards, okay, for various cases. That some of them were outside of the training data sets, and you'll see that it wraps around these baseline cases, but it could be going around and back onto it. If the rotation of the vorticity is not the right way, these rotation would go the opposite way around these manifolds. Okay, now look at this last case. This is a horrible case of the gust ratio being 10. That means the vortex is 10 times stronger in terms of its velocity compared to the cruise, right? You wouldn't want to be flying in here, and the wing is fixed at a particular location, but this one's pretty violent, but still does a really good job. Okay, and the reconstruction is really good too. Okay, now, all of these cases were trained with a single vortex impinging on the wing, right? Now, then we said, well, why don't we try this? In a real environment, we're going to be hit by many vortices. So let's just hit it with multiple vortices now, which will be a more realistic flying environment. And it turns out this particular model, because we have a CNN in there, does a fantastic job reproducing the flow field and capturing the physics even for multiple vortices hitting the wing. Because this filter that you have inside a convolution neural net, we're able to pick out these features and non-linearly reconstruct the flow field, right? So this was a pleasant surprise. We thought it was going to work, but it worked really well in these cases, okay? So this was very promising to us. So I asked about the 3D nature of this compression, right? So if you look at this manifold that we're discovering, you can argue that, well, I'm reducing to 3 variables, 3D, but what it really is you're projecting onto a 2D plane. So if I were to look from the top down, what I'm getting is I'm compressing all that information to R and theta only, right? So now you go from all that big data down to 2D, right? And on that 2D, we think there's some ways to analyze the flow field, right? Even though this is a transient flow, we're now looking at this physics in terms of phase dynamics. Okay, so this got us thinking on a few things about how to consider phase as part of our modeling effort. Okay. Now I'll come back to this phase dynamics because I'm going to spend a pretty good amount of time on phase. But let me also show another thing that was interesting about this autoencoder setup is now it's almost like plug and play. Okay, so let me give you an idea. We know about this manifold. Okay, what happens if I were to replace the input from the snapshots of the flow field to sensor measurements? So let's say I have pressure measurements, right, like in an actual aircraft, or velocity measurements. I would then feed that into Xi and see if I can tune the weight so that I can reconstruct the latent space, right? The decoder, I can use the same coder that I already trained, right? That turned out to be doable. And now what we have is a sensor input to a flow field output. So now we have the full state awareness that we can use. And this doesn't need, once you have this manifold, that is, you don't need the flow field, right, anymore, right? So there are different parts of the autoencoder that you can use for various engineering applications. Okay. All right, so let me go back to phase because I've been saying a lot about phase and these circles, right? If you look from a top down. So I'm going to go away from that original problem of a vortex hitting a wing, but I'm going to show you a slightly different or similar problem. We worked with our colleague at the University of Maryland, Anya Jones. Since then, she moved to UCLA. She's actually my next door neighbor now, but she has performed an experimental campaign where you have a wing, a flat plate wing. In this case, you're going from right to left, okay? This is a PIV flow field, vorticity field. And what's happening right now is it just went through a vertical jet, okay? So here, it's flying, okay? And then it's gonna enter, let me play that again. It's gonna enter a jet that comes from bottom, here it is. Then it separates massively, and then it exits the jet. And then that separated flow goes back to the reattached flow, okay? This, in my opinion, is a transient flow, right? But then Luke, or postdoc back then, said, well, it looks like a cyclic flow, right? It goes from one, which is the original attached flow, it enters this jet, and then it exits this jet, okay? And what he said was, why can't we look at this from a cyclic point of view? And how do we do it? We said, well, why don't we try persistent homology to see if we can find that cyclic relationship or that characteristic. And he was able to embed this latent dynamics on a circle, right, that he found through persistent homology and reconstruct the flow on a circle, right? This kind of makes sense, right? Because it's a cyclic event that's happening. You start from 1 to 2 to 3 entering the jet, have this massive separation, and go down to 4. So now you're compressing information on a circle, right? That's all we're doing. But it's pretty neat because instead of doing this transient analysis, now we can think of these things on an R theta plane, right? On a phase-like variable. And it does really well in terms of reconstruction, everything. Here is the measurements from a PIV flow field, and here's the actual reconstruction that we can achieve through these autoencoders, right? Now, why am I showing this? I got excited about this because what we're saying is the entire flow field can be compressed onto a representation of a circle, right? And on this circle, you can get different angles of attack mapped out, and you can even do an interesting thing where you pitch the wing and you'll have a various array of these trajectories, and what they are, or they are cross sections of a manifold, right? And what's interesting here is, let's say this is the original location where you started. Depending on the Gauss ratio that hits the wing, this circle will grow away from the original location, right? So this really captures the essential features of this complex transient dynamics that we were trying to understand. So what we're saying is we have some ways of representing the flow, we have some ways of modeling the flow now, okay? Now, why do we care so much about the phase? I also work on phase reduction analysis, and phase is pretty interesting in terms of how you can represent dynamical systems. Just to give you an idea, let's say you have a periodic event, okay? And that periodic event can be discretized from 0 to 2 pi, right? So here, let's say this is a governing equation, Q is your state variable, and you have a phase variable here, theta. Okay. Think of this as an Navier-Stokes equation. If you look at the rate of change of theta, if you're on the periodic orbit, that theta dot is simply the natural frequency of that system. Okay. If so, you know, just giving you a hint, if you go back to a transient problem, but if you don't look at it as a transient, if you look at it as a cyclic event, you can actually map all that to a circle, right? So that's why I'm kind of getting interested in this. And if you go through the math here, if you say theta dot is actually represented by a big theta, which is a phase function that lives not just on the limit cycle, but slightly outside of it too, you can write this as the gradient of theta dot q dot, right? Just calculus. And this q dot is from your governing equation, the right-hand side of your governing equation, f, right? So if you know the right-hand side of the governing equation and how sensitive your phase is, you can see that the dot product will be omega n. Okay, but if you change your f in some ways, you can see that omega n would change as well, right? And here's just an example of how we can visualize this for a simple flow. This is my favorite example of Reynolds number 100 cylinder flow, right? Periodic shedding. You can say if you plot CL and CL dot, you can see that it just rotates and rotates and rotates. And if you know what the phase is, you can always go back to the flow in this system, okay? Now, if you were to introduce a perturbation F, okay, that could change the phase here, right? So in this phase sensitivity function here, right, the gradient of phase, and you took the inner product, but this omega F could change how you could alter the frequency. This becomes really useful if you're trying to see how you can modify the synchronization property, okay? One of the biggest synchronization issues that we deal with as travelers is jet lag, right? Suddenly you're in a different location and you want to synchronize to the location's circadian rhythm, right? But you would synchronize, okay? Another thing you can do or analyze is a lot of biological signals in your brain. How do you synchronize the brain so that you would function normally or better? Right? These are the things that you can analyze with these. What we done is we took these theories and analyzed how we can synchronize the wake that's shedding to whatever signal you're trying to put in. It turns out this is a really well-established field, okay? One of the pioneers was Kuramoto. You might have heard of his name on a few equations. And there's even a theory to say, well, if you want to synchronize as fast as possible, what is the right optimal waveform? Okay, in those cases, instead of waiting for 20 cycles, you can figure out how to synchronize in 1 to 2 cycles, which is important for our problem because we're flying in a highly transient environment, right? So this is what Kai was doing when he was analyzing all those transient data, right? He analyzed how sensitive the flow field was to certain types of perturbations. In this case, he put in a jet at the leading edge or the very front of the wing and see how the flow could respond. And if you do so, this is the slice of manifolds. Here is the controlled and no control case. He was able to reduce those large fluctuations in lift by about, I would say, 40% or so. This, you know, the measurement's pretty strict, but roughly half, right? Now that's a really, you might say, well, it's only half. What's up with that, Sam, right? But this is significant for us because this happened within about 1 convective time units. That's about the travel of a wing, just 1/4 of a wing. And within that 1/4 length of travel, all this happened, right? This would be extremely difficult to achieve with standard methods because in standard control type methods for fluid mechanics, you're assuming that the wing is traveling 20 to 30 to maybe even 100 core lengths of travel. For us, that's too late because the vortex has already left. It's way downstream and we're being hit by another vortex, okay? All right, now, what are we doing now, right? I'm kind of, okay, I got about maybe 10, 20 minutes or 10, 15 minutes. So let me talk about what are the other efforts that we're looking at. We can also consider dynamic maneuvers, right? Here's a case where Hiroto was considering plunging motion, and it turns out based on different types of plunging amplitude, plunging frequency, you can identify different orbit patterns or something like a manifold that I showed earlier. What's interesting is that these orbits look like those atomic orbits that we learned in chemistry, right? So then you can pull out patterns. It's like, okay, here is how the wakes are behaving now, and that's quite different or orthogonal to other types of wakes. And by knowing those patterns, we can now make really nice models. Okay, so what the idea is that we're trying to find Zulu manifolds. And Nathan, I got the word zoo from you because in the past you were giving a nice talk talking about zoo of neural nets. So I stole that zoo from you. Okay, all right. And this effort also is now being extended to more complex flows like turbulent flows that I showed on my title slide. And this is going to be really nasty. I mean, if you look at the gust ratio 1 or 2, and if you look at the vortex hitting the wing for higher Reynolds number, so this is for 5,000, you can see that these vortices collapse and break apart really fast. But one of the nice things that we notice is that the large scale features are still the same. So even though we were looking at Reynolds number 100, a lot of the insights that we have gotten are still useful and can be transferred to the analysis at high Reynolds number. Just to give you an idea, if you look at much stronger vortices like gust ratio 5, this is an interesting case. This is a really bad case. A vortex hits and hits again. Okay, so you can see that you're going to get double peaks in the lift as you're flying in these really violent cases. Okay, if you were to now consider 3D wing effects, so this is what Hiroto is currently looking into, is let's say you fly into a column of a vortex, right? The dynamics is a lot more complicated than 2D, right? So I'm just going to show these movies. These are two different orientations of the vortices, so the rotating directions are different, but you can see how complex the wake becomes, okay? Through these analysis, we're actually able to get ideas as to which structures are important to rely on to reduce lift. That can be done by looking at force element theory. And another thing that was surprising, but yet really relieving for us, is that when you try to compress all that flow field information, different cases, it's still a low dimensional in nature, at least to get the dominant features of the flow. So here is Hiroto's effort to try to reduce all that information to three-dimensional latent space. Okay, and he's still able to capture the dynamics and also understand which directions the flow should be moved or altered so that the lift fluctuations can be minimized. Okay, so stay tuned. We'll get more results on these. Okay, and this is a collaboration with Steve's group that we just got published recently in Flow. Let's say you're trying to fly in a really unsteady environment like a cylinder wake. This is a 3D cylinder wake. Okay, you're trying to fly from red to green circles. Okay, in this case, if you don't take advantage of the vortices in the wake, you can't really make it to the final position. Okay, and some of you might be familiar with some of the two-dimensional work that was done by John Dabiri and John Dabiri's group for a few years ago. In 3D flows, you can take advantage of the streamlined vortices and kind of screw into those structures to get to your final destination in a very efficient manner. So, of course, you're going to be hit by vortices, and we're hoping that all the insights that we're gaining from the extreme aerodynamic analysis can be useful in further optimizing the flight pattern and stabilizing the flight too. This one right now is there's no interaction between the vehicle and the wake. It's just one-way coupling, okay? But this will be something we'll be looking into in the future. Okay, now, this is something I wanted to bring up as more as a teaser and maybe get some feedback on. The extraction of dominant dynamics for unsteady base flow is a major challenge, right? So a lot of you are familiar with POD or DMD type analysis, even stability, resolvent. They work pretty well for steady base flow. Now, the question becomes, well, what do you do for unsteady cases, right? And I'll even go to say, getting unsteady base flow itself is a challenge, right? It's not as easy as just simply solving for unsteady base flow. In many cases, you can't even solve for unsteady base flow. And if you were to just filter the flow in time and space, that may not be enough either, right? So we just published or compiled a paper that's now on archive. It's in press right now. We said, well, where are we? Where if we want to study unsteady base flows and the dynamics around it, we cover modal analysis, we cover causality, we cover optimal perturbation theory, all that. This is an area that I think we're going to be working on quite a bit so that it can help unsteady aerodynamics. Okay. One thing that's missing from this paper is we did not intentionally talk about machine learning because that's also a whole another effort that we can talk about. All right, just to give you an idea, if you have unsteady base flows, one of the biggest difference that you'll notice is the influence of acceleration and deceleration from the background, okay? Now, this is an example where Yonghwan Jung, or graduate student, was looking at how the vorticity would hit the flow, and according to those timing, what kind of perturbations can grow the most. We use the optimally time-dependent mode analysis, where we can actually track the modes and see which part of the flow is most sensitive, okay? Another thing we've done is we actually looked at a simple canonical case of a channel flow, but what happens if you were to accelerate or decelerate the flow? When you accelerate the flow, you can see that the growth rate of the flow field for certain types of modes increases by 10, okay? However, and this was kind of known experimentally too, but we confirmed it here, is if you have a decelerating base flow, you can have an explosive instability or amplification of your modes, right? And in this case, it's 10 to the 3, right? This one's 10, 10 times. This is 1,000 times larger in terms of instability. So as you're flying in an accelerating or decelerating environment, this tells you that in some cases, you might be able to break up structures if you can take advantage of deceleration, or stabilize the flow if you're going through an accelerating phase of your flight. Okay, so this is something we're really excited to explore more. I showed you a lot of dynamics in latent space now. Another effort that I got a chance to talk to Nathan a little bit is, well, how do you use that latent space information in another way? Another way we're doing, or another thing we're also looking into, how to look at designs of vehicles. And this is an effort not on the air vehicles, but this is a collaboration with the Honda Motor Company, where we're taking different types of car designs and compressing that information while we're trying to get some information about aerodynamic characteristics. Here we're showing drag. Sorry, some parts of this work is proprietary, so we're not showing the full extent of the work, but you can get other stuff out of this autoencoder type effort, okay? This is great because what you can do is you can compress all that information to a low dimensional space, and in that low dimensional space, you can do a design optimization. This is an actual example. This is a CRV, right, model. Here's an original design. It's digitized, so it looks a little choppy, but based on all the information that we have from a database, we can now automatically grow through the latent space and say, here are the regions of the body that we can change such that you would get better efficiency, right? Drag, lower drag. And this agreed very well with what the engineers have seen in the past, so they're very excited. Another thing that's really exciting is that because there's an automotive industry shift in terms of what they're trying to do from a conventional gasoline-based engine to motors, electric vehicles, or hybrid vehicles, the requirement for aerodynamics is changing quite a bit. And also what you can change inside a vehicle is changing. You don't have that engine that you have to cool anymore. So the front grille area requires a complete redesign. Okay, cooling requirements are different. The grill, you don't have to have same types of holes that would get the air in. And if you have a simulated vehicles in the past, you would know that to get the right aerodynamic characteristics, you have to simulate even inside that engine compartment. Okay, so this is a major effort that the automotive companies are going through. Okay, all right, so let me just conclude my talk. as an aerodynamicist, it's a really exciting time for me to be looking at these unsteady problems because it's not something that we traditionally dealt with. Now, it comes with a cost, right? You have to simulate a lot, or you have to do a lot of experimental measurements to see what kind of features that you're going to get into flow. This, to me, is a perfect place to use machine learning and data science to compress the information, understand the information, and act on that information. Okay, so that I've shown you some of the stuff that we've been doing for flow control and design optimization. And I think data-driven approach is going to further advance the field of unsteady aerodynamics or extreme aerodynamics. So I'll be looking forward to talking to you all more. And thank you for listening. Again, it was an honor to talk to you guys, and I'll be happy to answer any questions. Thank you.
Awesome. Thank you so much for that really incredible talk. We I'm almost speechless. It's so cool to see these low dimensional manifolds pop out of this. But yes, are there any
Thank you.
questions online or from the group here? I had a quick question regarding the autoencoders that you're using.
Mhm.
So when you added in uh, the consistency with the lift in
Yep.
the first autoencoder that you showed, you got a much better structure
Mhm.
of that like latent dimension. Had you also considered like directly putting like the parameters like the angle of attack into the latent dimension itself, that like some sort of like conditioned um uh encoding,
Yeah.
I suppose? Mhm.
Yeah, that's an excellent question and suggestion. We've actually tried that too, and you can get a good representation in some cases too. We There's another effort by or postdoc Barbara. She's looking at the effect of the wing shape. So you can have different types of wings come in to this problem, and in that case, she's feeding the wing geometry parameters into the autoencoder, and it could be on the input side or output side. You can do that, and you can get some compression or compressed latent space to behave or layer in a nice way, right?
Mhm.
Stay tuned because we haven't really finalized how we should do this well. But I think there's some room to play there too to get some nice interpretable data in the like this, right? Yeah.
Awesome. Yeah. And when you were doing this, you didn't put any like temporal information into the latent space either, right? You were just
No, no. So yeah, that's another excellent point, right? So this is just fed. So there's sequence of data just fed, but we didn't say that it needs to be, one after another. I've received a suggestion when I gave this talk recently at a different place was why don't you feed a movie, right? Instead of still images, can you deal with movies? And that's actually important, maybe a point to consider too. You can also um, set not just a lift function, but you can also say in the output side, try to get a set of ODEs. And you can do that too, so that you can get more dynamical information as well. But I think there's also room to grow in that area as well.
awesome. Yeah. Thank you. Any other
Thanks.
questions from the audience here or again in person?
Yeah, I'll be happy to answer afterwards too. I mean, by email.
Yeah, it looks like there's a
I have a quick question.
sure.
So, for example, in the more complex case, when you try to restore the state space, you may face the scenario that one vortex is hitting the wing,
Mhm.
while the aftermath of a previous vortex is also exerting on the wing. And in these kind of cases, can you separate the contribution to the lift, for example, between these newly coming vortex and the aftermath of previous vortex?
That's an excellent question. I haven't thought about that, but I'll give you my guess, right? It's very because this is a highly nonlinear flow, right? When you get separation, everything's really nonlinear in fluid mechanics.
Mhm.
Um, it's going to be difficult to separate out which one is from the first vortex versus the second vortex, right? Or subsequent vortices. So it will be, I think that will be difficult to say. Let's say some lift change in between is vortex one or vortex two, but I think we can identify um, in some nonlinear way how one is influencing another. Like you can I think one thing you can even, you can play God in some sense here is you can artificially remove one vortex and another vortex and see what the contribution will be like, or examine what the sensitivity is like. You can do that. But I also would want to give you a fair warning that there is an actual theoretical way to figure out what the contribution of each of these vortices are, right? From things such as force element or force partitioning methods. So I would say a combination of those two would be important for the analysis. However, once the vortex hits the wing, it's going to be generating secondary structure. It's going to generate shear layers. So at that point, there's going to be more than just say 5 vortices that I'm showing here. So it's going to be a little bit of a detailed, maybe an involved analysis, but you can certainly do these things.
All right, thank you so much.
Thanks.
And it looks like there is a question in the chat here.
Okay.
From Alexander. So the first question is, have you used usual autoencoders or instead like variational autoencoders?
We used a usual autoencoder or group. We kind of like to use the simplest thing possible. So
Yeah.
that's all we used. Okay. The variational autoencoder, we haven't used it, but we can probably play around with that too. So that might be the next step. I see another
And then
question. Opinion on the possibility or meaning to use these methods in a blood dynamics analysis? Absolutely, I think so. Hemodynamics is inherently unsteady. One of the things that's nice about blood or the pumping of blood is generally it's periodic, right? So you might be able to take advantage of that feature and compress it even further, right? But I think these are very useful. Another thing I would mention is that with adverse weather, it's not just flight that you're seeing unsteady effects, right? You are now operating engineering systems beyond their design point. And when that happens, bad things take place. For example, we also work with a pump company, and you might think pump is a very traditional machine. But if a pump fails, there's going to be major flooding in a city. And the reason why pump fails is generally because these operations are being pushed. Just to give you an idea, if you push a pump to operate beyond its design operation point, you can develop significant amount of unsteadiness upstream of the pump, and the pump is going to suck that unsteadiness through. And when that happens, the blades can hit the side, they can oscillate, vibrate, and destroy itself in some cases, right? So understanding the onset of these violent event is going to be more important, in my opinion, as you want to ensure that things don't fail, right? We don't want New Orleans to happen again after Katrina. And these events are happening all over the place. And these pumps, by the way, are no small pumps. They will fill up an Olympic-sized pool in 30 seconds. Okay. Yeah. So there are a lot of important problems out there.
Awesome. Any other questions? So I have one last question.
Sure.
So you said that you've created this very, very large data set, or perhaps even
Mhm.
sets of data sets. Are those publicly available for people to start playing around with? And is there a convenient place for them to find that?
Some of them are. The whole data set is a little heavy, so we
Yeah.
haven't like posted it somewhere. Especially for this crowd at UW, we'll be happy to share the data with you guys to play around with. So just ping me, and I'll be happy to go from there. Yeah, for sure.
Great, yeah. And are they only forward solves, or I know you mentioned sensitivities earlier. Do you have adjoints or derivative information at all?
Okay, so we have limited number of adjoints. We do have some information about adjoints too, so we can get those too for you, but they're not as extensive as the forward solves.
Gotcha. And what are
Mhm.
what are the sensitivities measuring for that? What are the
Okay, so we have the the actual adjoint simulation for the Navier-Stokes, and we also have the sensitivity and adjoint that we're analyzing for the phase dynamics too. So we have two sets of information.
awesome? Yeah, I know
Mhm.
those are tough to get. So it's
Yeah,
that's,
yeah, yeah, yeah.
yeah, great. Any final questions before we end here?
Right.
All right, well, if not, let's thank our speaker one more time. Thank you so
Thank
much.
you.
It's been incredible, and hopefully this starts a lot of conversations going forward.
Yeah. Okay, I appreciate it. Thank you so much for the opportunity. Had a
Yeah,
good time. All right, I'll talk to you guys soon.
yeah. Take care.